This question is going to be a bit of a slog, so if you've already got it and you're fairly confident, you might end up kind of skipping bits of my answer, which hopefully you've kind of twigged that you can do that with all my other videos as well. Obviously, it depends on where you are with your learning. Okay, I'm going to use a substitution. So I'm just going to go, they've told me what to do, I'm just going to go straight for it. So that means that x equals tan theta. So dx, d theta, that would be tan differentiates to sec squared. So that'll be sec squared theta. I'm just going to rearrange that so I know what dx is. Dx equals d theta sec squared theta. Okay, so I've now got something that I can substitute and sort of change the whole equation. There's an issue here, which is what do we do with the 0 and the 1? Now there's actually two different approaches. Some people change those values, and some people just leave them, but leaving them only works. Anyway, I'm going to leave them, so if you don't usually leave them, you might be like, whoa, what's Duncan doing? But you'll see how I kind of get away with it. And there's a reason I've chosen that approach, because my experience of teaching is that people, anyway, so if it's not the method you do, hopefully you might learn something and you'll understand how some other people do this sort of question. Right, let's go for it. So that'd be integral 0 to 1. Yeah, that is actually technically wrong, but hey. That'd be 1 plus tan squared, because we're using that substitution for the x, squared, and then we've got dx has become d theta sec squared theta. I'm just going to spot straight away, oh look, 1 plus tan squared is sec squared, so that would kind of explain why we've been asked to do this, I guess. I'm just going to get rid of that large logo. Now that's sec squared theta times sec squared theta, because that's what squared means. We could have written this multiple different ways. I've done it like that because it's just going to make it easier for me to cancel, because then I just can see that cancels. I'm just being really safe here, trying to make sure I don't make a mistake. Now that is the integral of cos squared theta d theta, because sec is 1 over cos. If you're not convinced, if you've got 1 over sec squared theta, that's 1 over cos squared theta, which then you might think of that as 1 divided by 1 over cos squared theta, which is 1 times cos, because we'll turn the fraction upside down, because if you divide by a fraction, oh look, which is cos squared theta. I'm aware that people at this, many people doing algebra at this level still like to think about fractions like that, so that explains why it's cos squared. Personally, I just see that if the fraction's on the bottom and it flips, it just brings the thing that's on the bottom to the top straight away. That's kind of a bit of experience there. So we're going to be integrating cos squared theta. So let's go for that. And we're going to need to watch the 0 and the 1 as well. How do we do this? We're going to have to use cos 2 theta equals cos squared theta minus sine squared theta, which is cos squared theta minus 1 minus cos squared theta. So that would be 2 cos, squared theta minus 1. So the integral from 0 to 1 of 2, whoa, almost made a mistake there. So I need to finish rearranging this, obviously, so then that would be 1 plus cos 2 theta times a half, because that's just a bit of quick rearranging there. Obviously be really careful if you do rearrange that fast. I plus 1 to both sides and I divided both sides by 2, and dividing by 2 is the same as timesing by a half, because that's supposed to be a half. I haven't written it very well. I'm going to put the half on the outside because I like to put constants on the outside, so that would be integral of 1 plus cos 2 theta d theta. Just put a box around that. So that's a half. That would be a theta plus 1 half sine 2 theta d theta. Now, the issue we've got here is, this is wrong. Oh, why have I written a d theta? The issue we've got here is, this is currently wrong. Because the 0 and the 1 were in terms of x. So we're going to have to use x equals tan theta. So this is where some of you are like, well, this is how I do it all the time anyway. I don't know why you're making a big fuss. Some people won't do it like this all the time. If you do it another way, keep doing it the other way, because that's my preferred method personally. But I just know that a lot of people find that confusing. Anyway, so let's just substitute back in. So that would mean that theta is tan to the minus 1 of x. So we'll be using this to make the substitution. So that'll be a half tan to the minus 1 of x. By the way, I should have put a 0 and a 1 there, but I forgot. Plus a half sine. So this is going to be a bit awkward. So basically it's going to be 2 tan to the minus 1 of x. Okay, so that's a bit strange, but there we go. 0 to 1. We need to put some numbers in here. I'm going to pause the video at this point, do this carefully, and then I'll rejoin you. So to you, it'll just feel like a moment, obviously. So I've magically added lots of numbers there. My final answer is this. Pi over 4 plus a half. It looks really messy. It is quite messy. Now, some of you, so hopefully that was useful. Pretty fiddly question. I'm just going to deal with one issue because I know it's going to be an issue for some people. Why didn't I replace this with tan to the minus 1 of 1, and why didn't I replace this with tan to the minus 1 of 0? And then use, maybe actually calculate that, depending on whether I was going to use radians or degrees, and then use those instead all the way through. That is what I personally would have done. Notice, if I can just get this to work, notice, oh look, that actually appeared in the answer. And the reason it appeared in the answer is because we then substituted in. If this conversation is this last bit is making no sense, don't worry about it. I just know it's going to be an issue for some people. So the idea is there's two different approaches. Approach number 1, let's just recap this again. Approach number 1 is, oops, hang on, is that you change the limits of the integration at the very start when you do the substitution. I personally prefer to do that because we now have a substitution in terms of theta. So probably we should change the limits to reflect that we're using theta and not x anymore. But ultimately this is just a technique, so if there's things that don't exactly ring true all the way through, you can argue it doesn't matter, and therefore it's okay to use approach 2. It can be argued because you just leave the limits technically incorrect, but it doesn't matter because you make sure that you substitute back in terms of x before you then use the limits. And then it's okay because those limits are the limiting values of x, and you've now got something that's in terms of x.